So here I have started a computer code that's going to carry out this update process to allow us to animate the motion of a projectile. This code is hosted on a site called Trinket. I encourage you to sign up for a free account on Trinket. There's a link to this code in the description of this video that you can open and follow along with me. You can either write your own code or you can start with my code, and you can use that to explore this problem and take it in a lot of neat directions while you're studying projectile motion. So the first thing we're going to do is define a function that carries out one update. So think of that one update as being one frame in an animation. I'm going from one point to another point. So I'm going from one picture to the next. That's how I'm going to be able to animate this motion. So in order to do that, I'm going to define a function. In Python, the way you define a function is just with def, and then you give the function's name. We're just going to call it animate because that is the thing we're doing, is we are animating. So I've written here some comments. You see these lines that are in green? These are what we call comments, meaning the computer is not going to read them. They are comments left behind for you and me. I wrote them this morning so that I would remember what to do in this code. But anything beginning with the hash mark, the pound sign, the computer's just going to ignore. It's going to assume that that is for us humans to read. It's going to move on to the next line as if it weren't there. So you can put anything you want in comments to leave yourself little notes for later. So the first thing we're going to do is calculate the forces on the ball. So we're going to have a ball. And we're going to say the ball's force. So the dot in the middle here is what we would call in the English language a possessive, right? It's the ball's force, the force on the ball. I haven't created the ball yet. I'm going to do that in a little bit. But the idea is going to be that the ball's force is going to be all the forces that are acting on it. Well, we already identified that we're first going to be interested in the force of gravity, the weight acting on the ball. I will eventually add more forces, but that'll come later in the series. We're just working on the basics right now. So I just need what we had earlier. I need the ball's mass times the gravitational field times y hat. And I need a negative out in front. Now, I haven't told the computer what any of these are yet. We're going to set those values later. Right now, we're just worried about the animation function, and we'll get all that stuff set up in a little bit. Maybe we'll make a note to ourselves of what to set up. We're going to need a ball.mass, and we're going to need a gravity, and we're going to need a y hat. Okay, I'm going to take care of those in a little bit. Next, we're going to calculate the ball's acceleration. Well, remember we had ball acceleration is just equal to the ball's force divided by the ball's mass. Now you notice I am going to have the ball's force defined. I have ball force equals here, meaning it's going to take all three of these quantities, multiply them together, put that under the name ball.force, and then I'm allowed to reference that later here. Again, I will need the ball's mass, but I'm going to have that defined before we use this function. So there you have it. You have acceleration equals force divided by mass. Now we'll update the ball's velocity. So remember, we had that the new velocity was equal to the old velocity plus the acceleration times delta t. So the way we're going to do that is just ball.velocity equals ball.velocity plus the ball's acceleration times delta t. I don't like spelling out delta t. It looks like deltat. I'm not even sure what delta is. So if y'all don't mind, we're just going to call it dt. So the d is going to stand for delta. Now this might look a little funny to you because we got ball.velocity equals ball.velocity plus some things. What on earth is going on there? Remember, this is not writing a math statement. This is writing some instructions for the computer to follow. What these instructions tell the computer to do is take the existing ball.velocity. Oh, that means I better define ball.velocity before we get to this function. I'm going to take ball.velocity here, whatever value that has, and I'm going to add to it ball.acceleration times dt. I'm allowed to do that because I can take those two values and add them together. That gives me a new thing. It's going to give me a new vector. I can save that name under any name that I want, and I'm just going to write over the name ball.velocity. I don't need the old velocity value anymore. Remember, we're going to use the new velocity to update the position. Well, I don't need this old velocity value anymore. I can keep overwriting it each time I run this animation. Now let's do the same thing here. We're going to update the ball's position, ball.pause, going to equal ball.pause plus same process as before, ball.velocity times dt. And I'm going to need to define a dt, and I'm going to need to define a ball.position here. I'm using the abbreviation POS for position just because that's going to be tied to the physical position of the ball in the 3D animation, and we'll get to that in a minute. And at that point, I'm done. I have done everything I needed to do in the update procedure. I have calculated the force, just negative mg. I have calculated the ball's acceleration, just force over mass. I've updated the ball's velocity. The change in velocity is just acceleration times the change in time. I have updated the position. The change in position is just the velocity times the change in time. These are all physics equations. These are all high school accessible physics equations that you've probably seen if you have taken or are taking a physics course. We're just writing them in a little bit different way for the computer to understand. Now that we're done, we can exit this function. We're going to tell it return and continue on with the animation. Now this function is not going to do anything itself. All we're doing is saying here is a list of instructions. So when I say animate, this is the thing you're going to do. You're going to go through these steps in order, and then you're going to return. Okay, well, we better create the ball, right? We're doing a lot throwing this ball around, so we should probably create it. Fortunately, this language we're using called VPython carries a sphere command. And so I can tell it ball equals sphere, and it will create a sphere. Let me click on run up here, the play button, to actually show you what this looks like. Here is our ball. All right, I just say ball equals sphere. There it is in glorious 3D with some lighting and shading and everything. If I want to rotate the view, I can right click and drag around, and I can rotate the sphere. I can also shift click to pan around, and I can use my scroll wheel to zoom out and zoom in. Now, nothing's happening yet, right? I thought we defined this animation function. Well, we defined it, but we have not used it yet. So we're going to need to use the animation function. Let's do a few other things first. The next thing we're going to need to do is set the ball's initial conditions and properties. Fortunately, I have a list of that here. We're going to need to give the ball a mass. Let's say it's a rather light ball. Let's make it only 0.1. Now, if you're in a physics class, by now you hopefully are asking what are the units on that. The computer actually doesn't use units. You get to pick what units you use. You just need to be consistent with them. So let's say this is in kilograms, just for the sake of being consistent. Well, if that's the case, then my gravity for here on Earth needs to be 9.8. That's going to be in newtons per kilogram, just like we had on these slides earlier. I'm going to need to define y hat. Now remember, y hat means up. It means just going one unit in the up direction. We're going to find this using the vector function. The way the vector function works is that you give it an x component, a y component, and a z component. I'm going to copy and paste instead of trying to spell component a third time. There we go. And so I just give it in order how much it points in the x, how much it points in the y, and how much it points in the z. Well, this thing is only going up, so it doesn't point anywhere in the x. It points 1 unit in the y, and it points nowhere in the z. And that's it. If you ask it to print for you y hat, it will display on the screen over here what this vector looks like, 0, 1, 0. That is y hat. That is the vector that points up. So up here when I have a negative attached to y hat, it's going to point down. Pretty straightforward. I will comment that out since I don't really need it printed. All right, what else do I need? I've got ball.mass, I've got gravity, I've got y hat. Oh, I need to define the ball's velocity. Let's do something really simple. Let's suppose we just toss it up to begin with. Again, velocity is a vector, so I'm going to use the vector function. So let's say we toss it up. So I want nothing in the x direction. Let's say I throw it up with 2 meters per second, twice the average walking speed, and this is going to be in units of meters per second. How about we do that? Now, again, I can run this. It's not moving because I haven't actually told the computer what to do with the velocity yet, so let's finish this up. And then for ball.position, let's just have it start. Let's have it start at the origin. Let's have start at 0, 0, 0. This is going to be in units of meters. Now comes my favorite part, setting up the actual animation. So the idea of an animation is that you are taking many pictures and stringing them together to create something nice and smooth that looks like it's moving on the screen. Each one of those pictures is one update in the animate function. So every time I want to move the ball, I need to call the animate function. So what I'm going to do, I need to define my dt. So I'm going to make my dt. Let's err on the side of making this big. Okay, let's make this one 1 second. That is going to be too big, and I'll show you why it's too big in just a second. And let's keep track of our time, right? So let's say our time starts at 0. The way we're going to animate this is with a structure called a loop. Up until now, all we've been doing is giving the computer instructions, and it's going to execute them line by line, one at a time, in order, straight top to bottom. A loop allows you to do something even better, because a loop allows you to give a block of instructions to the computer that it's going to repeat over and over again. My favorite type of loop is the while loop. Some people like other types of loops that we'll talk about another time, but I really like the while loop, because while tells the computer, I want you to repeat this process while the following condition is true. So like, for example, if I say while time is less than, let's say 10, I want this thing to run for 10 seconds. It's going to run while this condition is true, right? I start out with time 0. 0 is less than 10. It's true. The loop is going to continue. Now, what I need to do in order to tell Python that I want this stuff to repeat, I'm just going to indent. The indentation means it's in the loop. So indented means in the loop. There we go. And so what I'm going to do is just tell it to call animate. And animate. There we go. And so every time it goes through the loop, it's going to go once, twice, 3 times, etc. It's going to call animate another time. Now, I need to update time as well. So we're going to update the time to be time equals time plus dt. So we're just going to increment time forward by dt each time. And I also need to give this thing what we call an animation rate so that it doesn't blitz past me on the screen. So this is just going to be 1 frame per second. This is just the frames per second. You really don't have to touch the rate unless the animation is going too fast or too slow for you. Okay, we have set up an animation code in fewer than 40 lines. Let's click run. Again, we're going to start out with a loop, and this thing is going to update once per second for us. Oh, look, it fell down. I thought I set it to going up. Why is it falling down? Well, it's falling down because my dt is too big. So you notice how choppy that motion was. I need my dt to be smaller than this. And actually, I want one other thing on this that I forgot to set up. We're going to ask this thing to make a trail for us to show us the trajectory of the ball. We had that trajectory earlier. We're going to do that. Let's make this actually while time less than 5. There we go. What we're going to get now is a trajectory of the ball. You notice it just plummets straight down because my dt is too small. Like it's getting pulled down too quickly in that time frame. So let's make that a 0.1 instead. Watch what happens here. Now it's finally going up. My animation is moving a little bit smoother. It's still a little bit choppy though. Part of the reason is because this gravity, 9.8, is actually pretty strong in terms of gravity. So what we're going to need to do is actually make this dt much smaller. Let's make it a 0.001 instead. But now what's going to happen, you notice, is that the animation hardly moves because there's not much happening in 0.001 seconds. So anytime you decrease the dt, you want to increase the frames per second. So let's make it 100 frames per second now. Oh, look how smooth that is. Okay, what I'm seeing from this is that 2 meters per second is actually not very fast to be throwing it up with. So let's make it 20 meters per second. See how high we get there. Oh, look at that. Now we're going up and coming back down. I could also, make this ball smaller. It has a default radius of 1. Oh, in fact, we don't even come down yet. We just zip up. And then we don't come back down in that 5 seconds. So let's maybe make this, make it 20 seconds. Let's try that. There goes the ball up. You notice it looks like it's getting smaller. That's because the animation window is zooming out. It's just to give you an idea of the perspective there. I should be able to come down. Maybe I don't. All right, let's make it 100 seconds. And this is the part where it's interesting, right? I have a code that is doing what I want. It is doing interesting things, but I need it to do the thing that I want, right? Like right now, it's not really coming down appreciably. Or is it coming down now? I tell you what we're going to do. We're going to ask it to tell us when it is finished. Because I think it's still running there. Hold on. Okay, it is still running at that point. All right, I'm going to increase the frames per second by another factor of 10. There we go. Up. And then down. Okay, there we go. Oh, but look, it fell down below 0, right? It shouldn't fall down below the ground. So another way I could do this, right? I can make this condition anything I want it to be. I don't have to make that condition based on time. I could also make this based on position, right? I could make this based on the ball's position being above the ground. Now, how am I going to evaluate above? Well, I need to go to the y component. So that's going to be dot y. Let's say greater than or equal to 0, right? It starts out as a 0, so I should be fine to wait for it to be greater than or equal to 0. All right, now let's run. So now instead of keeping track of the time, I'm keeping track of the position, doot, and there it finally lands. So what I could do is ask the computer for how much time that took. Print, this took time, seconds. Ball goes up. Ball goes down. Doot. And there it finishes. Oh, I misspelled. Print. If you ever misspell something, Python is kind enough to give you an error message to tell you what to fix. I like the hang time that it gets there. That's kind of true. And that took just over 4 seconds. So here's a cool thing. And here's what I'll leave you with on this video. And then we'll get into the projectile arcing next time. How many of you in your physics class have a problem where you're given an initial velocity for a ball going up into the air, and you ask how much time does it take for it to fall down? You can solve that problem algebraically. You can. Or you can use a computer code. Get the computer to tell you. Pretty interesting stuff. All right, next time we're going to take a look at how to actually make this into a full projectile moving in 2 dimensions. Thank you so much for watching. I will see you next time. Bye-bye.